some point in the evolution of personal computers, it became clear that they would be used not only for professional use, for example in companies, financial institutions and education, but also would be used as centers of home entertainment systems, enabling users to play games, watch videos and listen to music. This led to processors being able to work with multimedia data. As the stereo sound has the form of a series of samples, and pictures are often represented by a matrix of 3 color pixels, the method of improving the performance of multimedia processing is to introduce parallelism. At the processor level, the answer is SIMD, single instruction, multiple data, which allows the execution unit to perform the same operation on many data units at the same time. Speaking more formally, one stream of instructions performs operations on many data streams. The first SIMD instructions introduced in x86 family that follow this idea are MMX, Multimedia Extension. MMX set of instructions operates on 64-bit packed data types. Packed means that the 64-bit data can contain 8 bytes, 4 words or 2 double words. Based on this, the new packed data types were defined, also called vectors. The principle of vector operation is that the same operation is performed simultaneously with many pairs of arguments. New 64-bit data requires new registers, called MMX. These are 8 MMX registers. Please watch our video on x64 registers to know more details. An interesting challenge appears in vector calculations. When performing arithmetic operations, the main processor stores additional information in flags. Key information for arithmetic operations is the carry when adding and the borrow when subtracting. The MMX unit doesn't have flags for each calculated result, so some other approach should be used. The simplest solution is to forget about a carry. It is simple, but it can give improper results. For example, if in addition operation the maximum value is exceeded, the higher bits of the result are truncated, so the result is reduced in value. In case of subtraction, the situation is reversed, and the resulting value will be larger than expected. This approach is implemented as a wraparound mode. For multimedia operations, a better solution is to limit the result to a maximum or minimum value. This approach is called saturation and comes in signed and unsigned versions. This means that, for example, when a pixel reaches its highest brightness, it will no longer be brightened. This way, information about brightness differences is lost, but the resulting image looks more natural. Let's have an example. If we have 2 vectors of bytes and we add 255 plus 1, it gives the result of 0. In unsigned saturation, anything we add to 255 gives the result of 255. In signed saturation, the maximal value is 127 and the minimal minus 128. And this rule applies to all elements of a vector. All MMX data processing instructions begin with a letter P, which is an abbreviation of packed. The suffix specifies the size of the element of the vector. Inside, there can be the letter S if instruction implements signed saturation, or 2 letters US for unsigned saturation. Let's have an example of various versions of packed addition. PADDB is packed addition of 8 bytes with wraparound. PADDW is addition of 4 words, and PADDD 2 double words with wraparound. PADDSB is packed addition of 8 bytes, and PADDSW 4 words with signed saturation. PADDUSB is packed addition of 8 bytes, and PADDUSW 4 words with unsigned saturation. We discussed how to handle the challenge with a lack of flags, but what to do if we lack of more space for the results of calculations? Multiplication operation requires twice as much space for the result as the size of the arguments. You remember that the results of multiplying, for example, bx by ax is stored in two registers, ax and dx. The solution for this issue is to split the operation into two multiplication instructions, storing the higher and lower halves of the results. For vector of words, the instructions are p-mul-hw, which stands for packed multiply with storing higher halves of the results, and p-mul-lw, packed multiply with storing lower halves of the results. Later halves can be joined together, forming full results with unpack instructions. To unpack the higher halves of arguments, the p-unpack-hwd, unpack from higher halves words to double words, instruction can be executed. For lower halves, the p-unpack-lwd instruction can be used. In our book, we will present the code for this. Another question we face is how to represent the results of comparisons. The set of comparison instructions allows for comparing values in two vectors. The approach is different from that in the main processor. You remember the CMP instruction sets flags depending on the result of the comparison. Here, we choose the comparison type, and the result is presented as a bit mask with all ones at the element of the vector where the comparison result is true, and all zeros in the opposite case. The pack and unpack instructions give us the ability to change the size of elements of vectors. We mentioned already two unpack instructions, but we have more possibilities. In instruction mnemonics, last two letters specify the size of the source and resulting vectors. For example, the instruction presented in a picture is a packed unpack higher halves from bytes to words. Pack instructions have similar built names. The instruction presented in a picture is pack double words to words with signed saturation. MMX makes it possible to shift arguments of a specified size left or right. The bitwise logical instructions are also implemented. They operate on a 64-bit data as a whole. MMX instructions are the first successful attempt to introduce SIMD vector processing in x86 architecture. The main problem was that they used the same physical registers as the FPU. As a result, mixing FPU and MMX instructions in the same fragment of the code is not possible. Switching between FPU and MMX in a code requires executing the EMMS instruction, which resets both units. Fortunately, newer vector extensions, including SSE and AVX, introduce a separate set of registers for improved flexibility.